last topic of dealing with the equations of chemical reactions deals with combustion and then an overview of all the reactions that we've done. So let's start with the combustion, also known as burning. When you burn something, you've got to have oxygen. If you have a candle burning and you put a lid on it, the candle eventually will go out because it will use up all the oxygen, and there's no oxygen to form the combustion form. So combustion requires taking oxygen and creating a reaction that will give you the same two products if we assume, wrongly so, but if we assume 100% efficiency. So let's take the burning of octane in a car. So this is going to be a combustion reaction because you're burning stuff. All right. Octane, as we know, is a liquid. Now, to be frank with you here, the car, even though there's an octane rating on the type of gas you have, most cars run off of fuel that has an octane rating of 87. The Supreme cars, the high-end cars, 92. Some cases 93. But that's because of some kind of complex computation in dealing with what we call isomers of octane. It's not pure octane. If you actually had pure octane in your car, it wouldn't run. It wouldn't have enough energy to burn. Anyway, but when you burn something, you're adding oxygen to it. Now remember, oxygen is a diatomic molecule. So don't just put O, you must put O2. Now, the thing about combustion reactions is that, like I said, you get the same product every time. And that is carbon dioxide gas. And now initially it starts off as steam, but when it cools off, it becomes a liquid. You put gas there, that's fine, it's understandable, because initially that's what it is. So you have to start with what we call an organic compound, meaning that you've got carbon and hydrogen, and in some cases oxygen. Not always. The fuel that you use from your gas tank is all carbon and hydrogen, what we call hydrocarbons. There are people who put some kickers in there that has oxygen in it, but you got to be careful because it runs really hot and your sensors get fried, and then you got all kinds of light things going on your dashboard. You don't want it. Trust me, I tried it. Anyway, so now it's just a balancing of equations. Now we've done these reactions already. We don't need to spend any more time because the practice problems for the balancing of complex equations for the 5 that we did were these types of reactions. But we'll do one more just to make sure we got it down. So we got 8 carbons, we got 18 hydrogens, and we got 2 oxygens. And over here we've got 1 carbon, we got 2 hydrogens, and we got 3 oxygens. Nothing's balanced here. And again, because we have oxygen in 3 different places, we're going to balance everything but the oxygen and do that one last. All right, so we got 8 here and 1 here. So I need to put an 8 there to make that an 8. We'll deal with the oxygen later. We got 18 hydrogens here. We got 2 over here, so that means we need 9 wah-wahs there. And that makes that 18 right there. The total sum of oxygens then is 16 plus 9, which is 25. So this becomes 25 halves. And that is your combustion reaction. Now, combustion reactions become pretty controversial recently. We've been using combustion reactions for a number of things for many years. The burning of coal. Burning of coal is a mixture of organic compounds or carbon compounds. Gasoline, like I said. This is the problem. They all create carbon dioxide, and carbon dioxide has been proving to be quite harmful to the climate, so we're looking at options of getting out of that. And so that's why they're getting away from what they call fossil-based fuels. Not completely, they'll never get completely away from it, but they're going to try and change it dramatically. So that's the history of that, why people have been talking about it. Now you understand whether you agree or not, I don't really care, it's none of my business, but that is what's being laid out there for you. These are the facts. Okay? What you do with them is something else. Now, let's go to the types of reactions. You should be able to look at a set of reactants and figure out what the products are. And you should be able to identify what kind of reaction it is so you know what the products will be. Let's take, for example, this one right here. Now, this is not reacting with anything, so that tells you that this is not a combustion reaction. The only thing that we can do with something that is a whole compound is break it down into parts. So what kind of reaction would that be? Yeah, that's decomposition. We're going to decompose this thing. So when you decompose a compound, you're going to break it down into its elements, into carbon and hydrogen. Okay? Now, there's a number of things we have to do with a reaction, with an equation like this. First of all, phases. What's the phase of carbon? It's a solid. What's the phase of hydrogen? It's a gas. By the way, if you were going to say that carbon is a gas, you're thinking of carbon dioxide, not carbon. Carbon is basically charcoal. Diamonds. There are some colorless diamonds, but most diamonds are black. Coal is black. It's a black solid for all practical purposes, with a few very minor, a low number of exceptions, which is why diamonds cost so much, because they are very rare. Regardless, next thing we need to check our diatomics. Is carbon diatomic? Well, you need to go back to that section where we talked about that when we dealt with the first balancing equations, first reactions for equations, which dealt with formation or synthesis and decomposition. I'll have it, there's a list on there. Carbon, however, is not one of those elements. Hydrogen, however, is. Which ones are diatomic? Well, if you take a look at the periodic chart, the best way to remember, it starts over here, hydrogen, then nitrogen, oxygen, and all of group 7A or 17. Carbon, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. We don't care about acetine. Acetine is not something we'll ever deal with. So now we balance the equation. So the line here, carbon 3, hydrogen 8, carbon 1, hydrogen 2. So with the carbon, we got 3 carbons here, 1 here. Put a 3 in front of the carbon, not behind it, because we're not making a new formula of the compound, and it's not something called triatomic. So the 3 has to go in front. It's a coefficient. We have 8 hydrogens here, 2 hydrogens here. So we put a 4 right there. That gives us 8, and now we have a completely balanced equation with a decomposition of C3H8. Okay?